Now the number what I've taken is 11. 11 is nothing but B. Now what goes to register R0 is B. Compare B with 10. It is higher. Now this statement will not be executed. Now R0 you have B plus hexadecimal value of 0. ASCII value of 0 is 48. Its hexadecimal equivalent is 30. Now this statement will not, R1 will not be changed now. That means this will not execute. So R1 is still 0. Now add higher or same. Now R1 is B. Is it higher than 10? Yes, it is higher than 10. Now ASCII value of A is 65. 65 hexadecimal equivalent is 41. 41 minus 10 is 31. 31 plus B it is. 31 B is nothing but 12. 31 plus 11. 31 plus 11 is 42. Now you should get 42 in register R1. So 42. Why? What is this 42? 42 is the ASCII value of 11. So 11 ASCII value is hexadecimal equivalent is 42. For A it is 41. For 9 it is 40 like that. Hope you understood this. Okay, go back to the presentation. Now this is another example, counting the vowels. So in high level language you write it like this: if C is equal to A, E, I, O, U, vowel plus plus. The same thing in assembly languages like T, E, Q. I'm just comparing C and A. If not equal, so C and A, if not equal, then I go for comparing this. If this is not equal, these two are not same, then I compare this. And again, this statement will be executed if this is not, these two are not same. This statement will be executed if these two are not same. This statement will be executed if these two are not same. And finally, and this statement will be executed, these two are not same. And this will be executed only if any one of this is equal, correct? And plus 1 will be added. Yeah, and this is another example which detects if C is a letter. If C is greater than or equal to A, and C is less than or equal to ASCII value of Z, then it is a letter, correct? Because it is inside A to Z, uppercase A to Z. And similarly, if C is greater than or equal to this lowercase a and less than or equal to this lowercase z, and again it is a letter, then I increment letter plus plus. And the same thing in assembly languages like this. And we have the conditions embedded here. I'm subtracting from the character which I give, the A, it goes to temp, and just comparing temp whether it is in this range. And sub I, if temp is higher than this 2 value, then I'm doing this. I'm just subtracting it from the lowercase a, and then compare I. So compare these two if the result temp value is I. So and add if lower or same, the 1 to the letter. So, and again I have the execution for this also, will show you. So in this example I have used the concept of register renaming or alternative names. Build, so debug. Okay. Yeah, observe now. C is the alternative name which I am taking for the register R0. Temp is the alternative name which I am taking for the register 1, and letter is the alternative name which I am taking for the register R2. Next, what I am moving to the register R0 is 66. 66 in hexadecimal is 42. That is the letter B. Now I want to check whether it is a letter or not. This is what I'm doing. To check 66 is a letter. 66 is the ASCII value, decimal equivalent of hexadecimal 42. and it is the ASCII value of letter B. So actually, strictly speaking, this is the letter. This is the letter. Now I want to check. How do I check? I have to check whether this lies between uppercase A to uppercase A. ASCII value is 41 and Z, correct, no? Uppercase A ASCII value to uppercase Z ASCII value, or if it lies in lowercase a to lowercase z ASCII value, then it is a letter. Now I'm checking. Now since it is an uppercase, yeah, it should lie in this range. Now subtract an I. So yeah, this is not I now because it lies in this range. So this is not done. Now temp is not updated, you can observe. Yeah, temp is yeah, it was 1 year only, correct, no? It is 1. Temp is not further updated. Now compare I, and nothing will happen. Now it will add. Now R2 will become 1. That means it's a letter. It's a letter. Now if I instead of 66, if I put 0, sorry, 48 is the ASCII value of 0. Now the register R2 should not be updated with 1. Now what goes to R0 is hexadecimal equivalent of this, that is 30. Now I'm subtracting. So temp is this. I'm comparing with this. Now subtract an I, because now this 48 is not in this range. Now I have to check whether it is in the range lowercase a to uppercase A to Z. Again compare. Now it is not in this range also. Now add. So lower R same. Now it will not add 1. Now this R2 will remain 0 itself. So R2 is 0 itself. 0. And since I have not written back B back, it's going back. It's okay. R2 is still 0. That means this is not a letter. It is a digit. What digit? 0. Hope you understood. Yeah, working example. Now looping constructs. You can basically write two types of loop: the loops which counts upward and the loop which counts downward. ARM loops are fastest when they count down towards 0. Now instead of using the up counter loops, it's recommended to use the down counter loops in ARM, because down count loops are much faster than compared to up count loops. Now here we understand to implement two things: down count loops efficiently in an assembly, and how to unroll the loop for getting the maximum performance. These are the two things which you'll understand now. So decremented counted loops. So n to 1, I want to perform some loop from n to 1 including 1. So this is how you can write: move n value to I. I is an alternative name to some register. Loop here. Sub is subtracting, and branch and greater than to loop. Now what this will do, from I is equal to n minus 1 to 1 including 1, so many times it will repeat. Similarly, if I want to go till 0, so same thing, everything. Now instead of branch and greater than, you got to do branch on greater than or equal to. Now it will take you till 0 inclusive 0. Now decremented counted loop, one more. Now subtract 3. This will go from n to n by 3 inclusive n by 3. Say for example, n value is 30. 30 by 3 is 10. It'll so many times, 10 times this loop is going to repeat. 10 times it's going to repeat. Now other counted loop. Now I want to use the negative index loop. This loop structure count from minus n to 0, inclusive or exclusive in steps of size. It depends on the step size what you give. Reverse subtract operation from 0, correct, no? 0 minus n I'm doing. Now I will be minus n. Loop add is, now this is step. Now it goes like this: I minus n, then minus n plus step, it goes like this. It's a negative indexed loop. This is also possible, and logarithmic loops are also possible. Here now n is equal to 4 counts down from 2 to 1 in powers of 2, something like this. Say n is equal to 4, if I take 2 raised to 4, that is 16, it will go till 1. If n is equal to 5, if I take 32 to 1, it will come 32, 16, 8, 4, 2, 1, it will come like this. Now to do that, I'm moving 1 to the alternative name to some register, that is I, and then left shift left logical by n bits. So here it is 4. So if I take 4 here, this loop is going to repeat for these many times: 16, 8, 2, 1. Now first it will be 16, 1, 2, 3, 4, 5. 5 iterations it will go. And similarly, there is another loop, which is the mask loop. It's something like here. Here also we have taken n is equal to 4. Now what this will do, it will count from 15, 7, 3, 1. Now I'm moving 1 to I, and then on I I'm doing since I've taken n as 5, 4 bit left shift. Now this I'll write and show you by opening the notepad. Here I is 1, I is equal to 1. Now on this 1, I'm shifting it 4 times to the left. If I shift it 4 times to the left, now first time when I shift left, I get 1 0. Second time when I shift left, I get 1 0 0. Third time when I shift, I get 1 0 0 3, and fourth time when I shift, I get 1 4 zeros. So this is what I get after shifting it 4 times to the left. Now that is what is in I. Now I is equal to this. Now I is equal to this after shifting 4 times. Next I come here, yeah, and then that is what is I, and that is reverse subtracted with 1. Now when I do, second here 4, okay, yeah, reverse subtracting I'm doing from 1. From this I got to subtract this. From this I got to subtract this. Now since it is we are taking only 4 bits here. Now this 4 bits I have to take. Now this is out. This 4 bits, if I take it as 0, so 0 minus 1, what we are doing, 0 minus 1, so this will give you f f f f. So 4 f's it will give. Now because it rotates, sorry, f it gives. Sorry, it gives you 1 1 1 1. That is nothing but f. Now that is 15. And next time inside this loop, your shift writing by 1 bit. When you shift write this by 1 bit, next what you get is, sorry, next what you get is, when you shift write this 1 1 1 by 1 bit, you'll get it as 1 1 1, sorry, yeah, and 1 0 added here to the left. 1 0 added here to the left. That is nothing but 7. And next, when you next iteration, this is again shifted right by 1 more bit, it will become 0 0 1 1. and next it will become 0 0 0 1. So now you have F, this is F, this is 7, this is 3, and this is 1. F is nothing but 15. It goes for 4 iteration. 15, 7, 3 and 1. Now this is the another example. Now unrolled loop, the same example which I showed you in the previous example, the same thing I've put here also. This particular loop is unrolled for 3 times in order to convert a single character from uppercase to lowercase. So loading all the 3 elements here, and these 3 will convert the first element from uppercase to lowercase. These 3 will convert the, now that means you have avoided using this BNE for 3 times. That means 3 into 3, 9 clock cycles you have saved. Now summary of looping construct. ARM requires 2 instructions to implement a counted loop. One subtract instruction must be there, and conditional branch should be there, and you can use the loop unrolling technique in order to improve the loop performance. And one more important thing here is the number of unroll. What you do is limited by the number of registers available, so that because on every unrolling you have to use the different registers. That means you cannot go for unrolling it for a large number of times. The number of unrolling what you can do is maximum 3 unrolling or 4 unrolling. Now ARM can implement this negative and logarithmic indexed loop efficiently. That is what I showed you. Negative loop also I showed you, and logarithmic loop also I showed you. That is logarithmic in the sense 16, 4, or 2, 1 when n is equal to 4. These kind of loops are also possible. This completes your module 2 completely. So from the next class onwards we'll see the module 3. I'm going to start with the module 3. Thank you.